Okay, you can start.
Good morning, everyone. This is Group 6, and we'll be presenting differentiation and integration. The members of Group 6 are me, myself, Samuel Chikambebu, including Miriam Abdurrahim and Victor Oluwasusi, but unfortunately, Victor dropped at the tail of this presentation, so he won't be presenting with us. So we're talking on differentiation and integration. And what our topic overview for today will be difference formula. Right after that, we'll also be looking at basic rules of integration. Then later on, my colleague Miriam will be talking to us about adaptive quadrature. And right while she will be talking about adaptive, she also include error formula to it. We'll also be looking at Gaussian rule and also composite rule. So we'll be proceeding. Differentiation. What is differentiation? Differentiation is the process of finding the ratio of a small change in one quantity with a small change in another, which is dependent on the first quantity. And where are areas where we can apply differentiation? We can apply differentiation in so many things. One of those things is in velocity and acceleration. That is why we have the diagram of a car standing in house A, and the car wants to make a move or a journey from A to B. So when the car makes this move from A to B, we can say the car has made a derivation. That means the derivative of that function where the car was standing, f of x, tells us about the instantaneous rate of change of the car, which we now say it is f prime x. This is also similar to finding the slope of a tangent to the function at a point. So let's consider that if y is equals to f of x that is differentiable, then that differentiation is represented as f prime of x, just the way we saw the car moving from f of x and changing a state or making an instantaneous rate of change to f of prime x. And this can also be said as dy dx as differentiation is concerned. And this is also, this dy dx is also the a general expression of a derivative of a function where y is equal to f of x, which is any function. Then what are the basic rules of differentiation? We'll consider some basic rules of differentiation. One of them is constant rule. Another is a power rule, then sum and difference rule, then the derivative of E. When we consider all this, we can actually put them together and sum up something about differentiation. So let's look at constant rule. Constant rule states that the derivative of any constant is 0. Let's take for an example. Example 1. If we differentiate the function f of x equals to 4, 4 is actually a constant. So when we differentiate it, we will get a 0. If we differentiate a function, looking at example 2, sine 5, when we differentiate it, we will derive a 0. When we differentiate the function f of x equals to 6 open bracket 5 minus 7, close bracket in cube divided by 14. They are all constants. There is no function of x in them. When we differentiate this form of differentiation, what we'll get is also a 0. So let's look at power rule. Power rule states that if we have a function of x to a power, we'll simply multiply the whole function by that power and reduce that power by 1. Let's also consider this example to make it very clear to us. So if we differentiate the function f of x is equal to x squared. Now, our power rule states that if we have a function to a power, we'll simply multiply the function by that power and reduce that power by 1. So let's multiply the function by the power f of x, which is equal to x squared. We can see that 2 is on top of x. If we bring down the 2 and multiply by the function x, then reduce the power by 1, which is 2 minus 1. What we'll get will become f prime x equals to 2x. If we also consider this example 2, and we differentiate the function f of x, which is equals to 5x to the power of 4. If we follow our the rule of a power rule, he said we should multiply the function by the power. So we'll bring down 4 here and multiply it by 5. Then we reduce the power 4 by 1. This gives us 20x cubed. So let's notice how the exponent is multiplied by the function and the power reduced by 1. This is just simply what power rule is telling us about. Then let's look at sum and difference rule. Sum and difference rule state that if we have a function of more than one term, it can simply be differentiated term by term. Let's look at example 1 for an example. So if we have a function f of x equals to 4x plus 3x squared, sum and difference rule tells us that let's take them term by term. So if we want to differentiate this example, we'll look at 4x. If we differentiate 4x alone, what we'll get is x. And while we're looking at the example of the power rule example, we can also bring that rule into play in this area. Then we'll multiply this x squared, we'll multiply this 2 by 3 to the x. So what we are going to get is 6x. This same difference and sum and difference rule, we can also apply it in this example 2. All we just need to do when we differentiate the function f of x equals to 5x squared plus 16x, we'll differentiate them term by term. We'll bring these 2 down and multiply it by the function. Then we'll reduce the power by 1. So here we have 10x plus, looking at 16x. When we differentiate 16x, what we have is 16. So therefore, our answer in this place is 10x plus 16. Let's also consider the derivative of e. the derivative of e to the x power is e to the x. This is because e to the x is a function such that every point on its graph is also the slope at that point. So if the exponent has a constant along with x, do not reduce the power as you typically would when differentiating. When we did power rule, we said you can bring down the power down and multiply by the function. But for the derivative of e, we just have to let it be the way it is, unless it is the power is multiplied by a value. So let's look at example 1 in this derivative of e. If we have a function f of x equals to e to the power of x, the derivative of e says we should leave it the way it is. So we are going to leave this one the way it is. And when we look at the second example 2, we said the function f of x is equals to 5x raised to the power of x. The rule still remains the same. We are going to leave it the way it is. But what if this power that is raised, this x that is raised to a power has a value by the side? Let's look at another example. So if we have a function 4x, equals to, if we have a function s equals to 4e raised to the power of 2x. In this case, this 2 will remain, but we are still going to bring down the this power to multiply it by the function. So when we differentiate this kind of differentiation, what we have is 8e raised to the power of 2x. Now we move to integration. When we integrate the derivative of a function, we get back the original function as the result. What integration means is integration is just the reverse of differentiation. If we differentiate whatever we get as our derivative of f of x, when we reverse it, what we are getting is the integral of that function. That is why we have f prime x will give us the original function f of x. So let us consider one of the examples we treated in our differentiation. So if we have f of x equals to 2x, what this is simply telling us is, since we know how to differentiate, we can state that 2x, when we integrate it, what we are going to get is x raised to the power of 2. Now we have f of x, capital F of x in this form. What we are just trying to tell you is that f of x is an antiderivative of f of small f of x. When we see that the upper f in f of x, what it means, as I've stated, is just telling us that it is an antiderivative of f of x. And based on our knowledge on what we have spoken about antiderivative, we can also see that capital f of x is x raised to the power of 2. And this is not just only the possible antiderivative that we can get in this kind of equation. Since any constant we differentiate to 0, we can also say that f of s could also be s squared plus 5. Or we can say that s squared we can say that s squared minus 2. Or we say s squared plus or minus any constant. taking this into account, the antiderivative of f of s equals to 2s is given by capital F of s equals to s squared plus c, where this c can be any constant. So let's see, let's look at this. Finding an antiderivative is also called solving a differential equation. So a differential equation is any function that is represented as a derivative of that function. So let's look at this first example. If we find the general solution of the differential equation, dy dx equals to 3x squared. We can say that y equals to 3x. First, that's what we are going to do first. We need to determine an antiderivative of that function, y is equals to 3x. Next, we need to take into account any constant which says y is equals to 3x cubed plus c. C standing as a constant. Sorry, I'm having this thing block my screen, so I need to move it away. So if we have can you hear me? Is anybody hearing me?
Yes. What's the problem?
Okay, I'm having something from the app blocking my view. So I'm trying to move it across the screen so I can have a visual of what I'm presenting. So let's see an antiderivative notation. When solving integration problem, it is more convenient to use the following notation. This is the notation of an integral, showing that the integral f of x dx, this is read as the integral of f of x with respect to x. Y dx means that x is the variable we are integrating, and f of x is the function we are integrating. Now, as I stated before, that integration is just a reverse of differentiation. So when we integrated, when we differentiated, if we want to integrate, it's just for you to do what? To do a reverse of that differentiation that we have. So integrating can also be referred to anti-differentiation or anti-derivative, which I've been using all the while. So what are differentiation and integration? Differentiation and integration formula are complementary to each other, just as I've stated before. Then differentiation is used to break down a function into parts, while integration is used to unite those parts to form the original function. Let me just use a simple illustration of saying, if we go to a restaurant and we ask for a plate of rice, and the rice was added, a beans was added, meat was added, probably mama was added. If we want to differentiate that whole bowl of food, we'll pick out the beans, we'll pick out the rice, we'll pick out the meat, we'll pick out the moi. This is just, we are differentiating that food. But if we want to integrate them together, then we will have to bring the rice, the beans, the moment we add them together, which tells us that we have integrated that food and we have made it just as one. Geometrically, differentiation and integration is a formula used to find the slope of a curve and area under that curve respectively. Then we can also say that differentiation and integration are branches of calculus where we can determine the derivative and integral of a function. Then we can find the differentiation and integration of a function at a particular value within a particular range of finite limit. Then integration of a function is done within a definite and finite set of limits, which is called a definite integral. So let's go to our topic proper, where when we are considering our topic overview, so we'll be looking at difference formula. So the most commonly used differentiation formulas are product rule, quotient rule, higher order derivative, trigonometric function, and the natural logarithmic function. So we'll consider them one after the other. So let's look at product rule. Product rule is used when we have two differentiable functions multiplied together. So if we have a product d dx, f of x, and g of x. So what we are going to do, we'll say let me state this product rule again. D over dx, f of x, gx is equals to f of x times f of prime x plus gx times f of prime x. This is what product rule is. So we have to apply this rule. To apply this, we need to write the first function times the derivative of the second, then add the second times the derivative of the first. That is, for us to apply this rule, f of x times gx, we have to first of all write the first function, then the derivative of the second function plus the second function times the derivative of the first function. Let's look at this in this example. Let's differentiate the function f of x equals to x squared plus 7 times 2x cubed minus 5x. First of all, what we'll do as regard to product rule, we need to pick the first function. Our first function here is this 2x squared plus 7. We'll write it down in this form. Then we differentiate the second function, which is 2x cubed minus 5x, which is this. Then we now plus the second function and differentiate the first function, which is this. So what we have here now is when we included our first function, we said 2x squared plus 7. Then we differentiated our second function. Our second function will give us 6x squared minus 5, which is what we have here, plus our second function, then the differentiation of our first function, which gave us this. Then our answer in this in this is 2s squared plus 7 times 6s squared minus 5 plus 2s cubed minus 5x times 8x. This is what product rule tells us to do. Then we
Mr. Sam?
Yes, I'm with you, sir.
Yes, the last page that I just exited from, the last derivative.
Yes, sir.
I think it has been cut off from the slide. We can
Okay.
barely see that. So probably when you are done, you could shift it up so that we can be able to see your f prime of x to be equals to 2x squared plus 7, bracket open 6x squared minus 5 plus 2x cubed minus 5x, and bracket open x. So I think you should move it up a bit.
Okay, sir. I'll do that, sir. Should I do it now or I should proceed?
When you are done, not now.
Okay, sir. So if we proceed, what we are going to have is 24s raised to the power of 4 plus 22x raised to the power of 2 minus 35 plus 16x raised to the power of 4 minus 40x raised to the power of 2. If we remove the parentheses, what we are going to have will be 24x raised to the power of 4 plus 22x raised to the power of 2 minus 35 plus 16x raised to the power of 4 minus 40s. So we have to, if we combine like terms, you can see we have 24x raised to the power of 4 and 16x raised to the power of 4. So if we combine these like terms, we have 40x to the power of 4 minus 18x raised to the power of 2 minus the constant 35. So let's also consider another example that states that if we differentiate the function f of x equals to s cubed times e raised to the power of x. So if we want to apply product rule in this function, product rule, as I've stated before, we have to do the derivative of the first function, then the derivative of the second function plus the second function and the derivative of the first function. So in this regard, we have s cubed, then d dx times e raised to the power of x plus e raised to the power of x, then d dx times s cubed. So let's let me move this away. If we apply the differentiation on this, what we are going to have is x raised to the power s cubed times e raised to the power of x plus e raised to the power of x times 3 times 3x raised to the power of 2. When we simplify this, what we are going to have is s cubed times e raised to the power of x plus 3s squared times e raised to the power of x. If we consider another example, when we differentiate the function f of x equals to 4x sine x, and we want to apply the product rule on this function. Now we can see that we have 4x sine x. So if we apply product rule, what we are going to have is 4x d dx sine x plus sine x d dx times 4x. So if we differentiate it, we'll derive 4x cos x, which is the derivative of sine x, plus sine x times 4x. So if we simplify this, what we will have here is 4x cos x plus 4 sine x. If we also consider quotient rule, we can see that quotient rule is used when we have two differentiable functions divided by one another. So let's see this basic formula that says d dx times f of x divided by gx, which is equals to gx times the derivative of f of x minus f of x times the derivative of g, that's g prime x, divided by gx raised to the power of 2. Now, if we look at this, we'll see that the bottom times the derivative of the top minus the top times the derivative of the function all over the bottom square. So this is just what we are trying to say, that is the bottom, which is gx, which you can find here, multiplied by the derivative of the top minus the derivative minus the top, then the derivative of the bottom all over the bottom squared. A simple example can tell us what this is. So if we consider the function f of x plus 1 divided by 3x squared, if we put the quotient rule formula into this example, we have 3x squared, which is the bottom, multiplied by the derivative of the top, which is 5x plus 1. Here we will now say it is d dx 5x plus 1 minus the top, which is 5x plus 1, multiplied by the derivative of the bottom, which is d dx 3x squared divided by the bottom squared, which we have 3x squared. So let's proceed and see.
Hello, sir.
Yes, I'm with you.
Yeah, by the time you look at your quotient rule, the initial formula,
yeah,
where you have gx squared, and on your example, underneath you have your gx to be what? To be 3x squared.
3x squared, yes, sir.
So I feel that bottom should be raised to another power square.
Another power square. You're correct, sir.
Oh, okay.
Yeah, we'll correct that, sir. So okay, yeah, sir. Here it is corrected. We can see that it has been applied. Yes. So I would make that correction in that other slide. So here we can see here that it is applied in this form. So if we differentiate this, what we are going to have is 3x squared multiplied by 5 minus 5x plus 1 multiplied by 6x divided by 9x raised to the power of 4. So if we multiply through, what we are going to have is 15x squared minus 30x squared plus 6x divided by 9x raised to the power of 9. Then when we combine like terms together, what we are going to have is minus 15x squared minus 6x divided by 9 raised to the power of 4. So if we factor out minus 3, because 3 can actually go in all this, what we are going to have is minus 3x times 5x plus 2 divided by 9 raised to the power 9x raised to the power of 4. So if we divide out 3x, what we are going to have is minus 5x plus 2 divided by 3x cubed. So if we consider our higher order derivative, we've talked about derivative. So higher order derivative, what is just telling us is that when we differentiate a function, we can actually differentiate that function the second time, then we differentiate that function the third time. We can also differentiate the function the fourth time up to the nth time, for the fact that we can keep on differentiating. That is what higher order differentiation derivative is only trying to tell us. So we know how to take some derivative, but if we want to find the second derivative or more, to do that, we simply differentiate again. That is, when you differentiate the first function, if it is still differentiable, we have to differentiate again, the second, the third, the fourth, up to the nth time. We can keep on differentiating. So let's consider this example. So if we have a function f of x equals to x raised to the power of 4, here we can differentiate the first function to be 4x raised to the 4x cubed. We can also differentiate it again to give us 12x squared. That's the second derivative. Then we can differentiate the third time to give us 24x. So we can see that if we keep on differentiating, for the fact it allows us, that tells us that function is an higher order differentiation. So let's consider the trigonometric function and the natural logarithmic function. So below is a derivative of a basic trig function. 1, d dx times sine x, we can derive it to be cos x. The second one, if we differentiate d dx cos x, what we'll get is minus sine x. And if we differentiate d dx tan x, what we'll get is sec square x. If we differentiate d dx times CSCX, what we'll get is CSCX cot x. So if we differentiate d dx sec x, what we'll get is sec x tan x. If we differentiate d dx cot x, what we'll get is minus CSCS square times x. Now let's go to the basic rules of integration. We have some basic rules of integration we can consider. One of them is when we integrate a constant, when we integrate 0, what we are going to get is a constant, which is when we integrate 0 dx, what we get is a constant. When we integrate k dx, what we'll get is kx plus a constant. And when we integrate k multiplied by the function of x dx, what we'll get is k integral f of x dx. When we integrate function f of x plus or minus g of x dx, what we are going to get is the integral of f of x dx plus the integral of g of x dx. When we also integrate f of x raised to the power of n dx, what we will get is x raised to the power of n plus 1 over n plus 1 plus constant, where n is equals to 1. When we also integrate cos x dx, what we are going to get is sin x plus x. When we integrate sin x dx, what we are going to get is minus cos x plus x. And when we integrate sec square x dx, what we are going to get is tan x plus c, which is a constant. And when we integrate sec x tan x dx, what we are going to get is sec x plus c. And when we integrate cs square x dx, what we'll get is minus cot x plus c. And when we integrate cx cot x dx, what we get is minus cscx plus c. Let's take note of this, that one, any constant in an integral can be factored out. This can make solving an integration problem much easier. So let's look at this. If we integrate 4x minus 4x divided by 25 dx, if we factor it out, we'll take out minus 4x divided by x and put it behind the integral of x dx. It will make our integration very simple. Then 2, we can, well, 2, integral may be split up into 2 separate integrals if the function being integrated consists of multiple terms. Let's take a look at the first one, which is a here. When we integrate 2x plus 7 dx, we can split them and integrate 2x dx plus 7 dx. If we do this, we will make our integration much more simpler. If we look at the second part, which is the integral of 3x squared minus 6x plus 5 dx, we can split them to have 3x squared dx minus 6x dx plus 5, the integral of 5x dx. And we can also rewrite our integration. We can rewrite our integration before integrating. It helps us to rewrite a function to get it into a form which is easier to integrate. So let's look at this simple example. If we integrate 1 over x squared dx. What we are going to do, if we have this kind of problem to solve, what we are going to do, we can rewrite it. We integrate, to integrate this, let's rewrite it. Let's say the integral of x minus x raised to the power of minus 2. What we are doing is we are simplifying this and we are making it x raised to the power of minus 2 dx. After we have done this, we can now integrate it. When we integrate it, what you are going to get is x raised to the power of minus 2 plus 1, which is x to the power of minus 2 plus 1 divided by minus 2 plus 1 plus a constant. When we simplify this, what you are going to get is 1 raised to the power minus 1 divided by x plus c. Let's look at another example. When we say find the derivative of 4x, we can factor out the constants. When we integrate 4x dx, what we have is we bring out the 4, then we integrate x dx, which we can write as x. This x is also, it also means x raised to the power of 1. So we can write it as 4 integral 4x raised to the power of 1 dx. When we use the power rule, where n is equals to 1, we can say that 4 times x raised to the power of 2 divided by 2 plus 1. When we multiply it, what we have is 4s squared divided by 2 plus the constant. And when we simplify it, what we are going to get is 2 times x squared plus c, which is a constant. So at this point, I want my colleague Miriam to handle adaptive quadrature and error formula.
All right, thank you, Sam. Good afternoon, everyone. So I'll be talking about adaptive quadrature. But before I proceed, I want to plead because there are some mistakes that I will actually correct after the class. So I'm really sorry, sir. So let's continue. When we talk about adaptive quadrature, we are saying that it is a numerical integration method in which the integral of a function is approximated using static quadrature rules on adaptively refined subintervals of the region of integration. So what are we talking about? Now, basically, when we are talking about adaptive quadrature, we are talking about using intervals. And when you split these intervals, then we'll get subintervals. Let me give an instance. If you have from 0 to 20, they are saying that you have an interval between 0 to 20, and you want to get the subintervals. So the subintervals between 0 to 20, that means you are going to have 0 plus 20 divided by 2, which is 10. So in between 0 to 20, we have subintervals 0 to 10 and 10 to 20. I don't know if you all get that. So that's basically what adaptive quadrature is talking about. So then we said we have the importance components of the quadrature. That means we have formulas that we use in getting this quadrature. So the first part is we have that's integral from a to b, f of x dx is equals to s f of a comma b. So please, can we go to the next slide? Sorry. Okay, this particular formula, the one you wrote error formula, that's the formula that is supposed to be up. I'm really sorry, sir, for the mistake. We'll fix it, sir. So that's the formula. Now, this h raised to power 5 divided by 90, f raised to power 4, mu and the likes. So this is the error formula. So that particular error formula is splitted when they did the what's it called? proving, yes, they go to 1/15, the one that is up, 1/15, S, F, A, yes, A, comma, B minus the sub-intervals. So let's give an instance of what we have been talking about. Please, the next slide. That we want to approximate the equation below with an error less than a tolerance, a specified tolerance. So if I is equals to the integral from a to b f of x ds, then what are we going to do using adaptive quadrature? It says that you compute two approximations. That means the first approximation, which is the intervals you were given from a to b. Now, after computing these values, you have to get a specified value. If you do not get this specified, that means if you estimate the error, if the statement is less than this specified tolerance, we are done. But if it is not less than it, that means you have to what? You have to get the sub-intervals, which is the sub-intervals I talked about from 0 to 10 to then 10 to 20. So that's the same interval. That is a comma a plus b divided by 2. That means you are getting an interval from a to b. That means you are getting an interval from a to b. So in between a to b, you get a, we want to get the interval. That means we'll have a plus b divided by 2. So we specifically say that a comma a plus b plus 2, that's the first subinterval. And the second subinterval, a plus b over 2 comma b. So now, then how do we get this particular S f of a? Then the first approximation, the one we want to compute. It also has a formula, and this particular formula we are using is the Simpson rule. We also have other rule, but the one we are basically specifying on is the Simpson rule. So please can we go to the next slide? Okay, so and the rule says that we have h over 3 open brackets f of a plus 4f a plus b over 2 plus f of b. Now, our value, that means h over 3, where h over 3 is b minus a over 2. That means we must have been given some intervals, just the way they gave us from a to b, which are these particular intervals. So you subtract these intervals and divide it by 2. That is how we'll get our value of h. So this is an example that we have the integral from 0 to pi over 2 sine x ds is equals to 1. Just like my colleague has explained integration, that if you integrate sine x normally, you are going to be getting minus cos s. Then when you get minus cos x plus c, and you impute the value of pi over 2, that's the interval from 0 to pi over 2, you should get the value of 1. But now, when we want to make use of adaptive quadrature, how do we solve this particular question? Now, the first thing we are going to do is we are going to get the exact interval. That means the interval they gave us to work on, which is pi 0 to pi over 2. Now, when we are working on this interval, how do we go about it? Please, I'll go to the next slide. Okay, so we have h over 3. First, how do we get our h? The interval they gave us is pi over 2, which is b minus a. So pi over 2 is regarded as a b, while 0 is the a. So we have pi over 2 minus 0, and that's pi over 2. Then divided by 2. So when you divide by 2, that will be times 1 over 2. Then you get what? Pi over 4. Now, inputting this pi over 4 into the value of h over 3, that means we are saying that pi over 4 divided by 3. And if you do that in normal multiplication.
Hello.
Yes, sir.
Yeah, you are too fast, and it appears that one is lost in some of your explanation.
I'm sorry.
I think when you were explaining the concepts, well, probably we're waiting that when we get to an example, we'll be able to get your thoughts. But you appear to be too fast. We don't understand how you are getting your pi over 2 times 0, and you just appeared at pi over 4. So I think that needs to be explained in at least a manner that one will understand it clearly.
Yes, sir. I'll take it again. So I said that when you want to get the value of h, it is h is equals to b minus a over 2. So I said that the value of b and a are the intervals that will be given in the question. So the question says that the interval is 0 to pi over 2. So it's 0 to pi over 2 at the interval. So automatically b is equals to pi over 2 and a is equals to 0. So now, and the formula says h over 3, open bracket, f of a plus 4f of, I'm sorry, there should be a 4f there. 4f of a plus b over 2 plus f of b. Now, the value of h will now be b minus a over 2. That is pi over 2.
Yeah, has
I
that
can't
fellow
hear.
gone out?
I can't hear her again.
Probably she has a problem with the audio. Well, I think that's a network problem. I'm still here.
Can we give her time? She wants to reconnect. She's back.
I'm so that's the net. So that's if you say pi divided by pi over 2 minus 0 divided by 2, we'll get pi over 4. Then pi over 4 divided by 3 is going to give us pi over 12. Now, our f of a, that means anywhere you see the value of a, that means you'll be imputing 0. And anywhere you see the value of b, we will impute pi over 2. Now, the first one is f of a. And the question says sine x. That means x in that value will be f of a. And our a is 0. So we say sine 0 plus 4 sine a plus b. That is 0 plus pi over 2 divided by 2 plus f of b, which is sine pi over 2, since our b is pi over 2. So we'll proceed from here. That sine 0 will give us 0. Then 4 sine 0 plus pi over 2 is pi over 2 plus sine pi over 4. So if you have, it is supposed to be, so when we multiply these particular values using the radian part, we'll get 1.0022279877492210. Now that is the interval they gave us. Now what adaptive quadrature says that we are going to split these intervals into two. That means after getting the specific one that they gave us, which is 0 to, we'll have to get the subintervals. And the subintervals from this will be 0 to pi over 2. If you divide that, that is 0 plus pi over 2 divided by 2 to get the subintervals. That will be pi over 4. Please, can we go to the next slide? That would be pi over 4. So we say that the subinterval, then pi over 4 to pi over 2. Now, working on the subintervals now, we have That means to get our, remember the formula is h over 3, f of a plus 4f, a plus b over 2 plus f of b. Now, to get the first h using the 0 to pi over 4, we are going to get 0 plus pi over 4, sorry, pi over 4 minus 0 divided by 2. And pi over 4 minus 0 divided by 2 is going to give us pi over 8. The subinterval for pi over 4, comma pi over 2, that's b minus a over 2. That is, a is pi over 4 and b is pi over 2. That is pi over 2 minus pi over 4 divided by 2. So when you multiply it, you get pi over 2 minus pi over 4. You are going to get pi over 4. Then divided by 2, that's times 1 over 2, which is pi over 8. So for a 0, pi over 4, we are getting pi over 8. And for pi over 4 to pi over 2, we also get pi over 8. Since we got the same pi over 8 for both answers, then we can work both of them together. That means the two subintervals. Now, having formula, that will be h over 3, and our first value is pi over 8. That's pi over 8 divided by 3. And that we should. Now, the first value for the first subinterval is 0 to pi over 4. So the a is 0 and the b is pi over 4. So for f of a, we get sine 0, which is 0, plus 4f, a plus b, that is 0 plus pi over 4 divided by 2. And that will get 4 sine pi over 8 plus sine pi over 4, which is f of b, that's sine pi over 4. Then moving to the second one, plus, we also get pi over 8 for the second interval, which is pi over 4, comma pi over 2. Now, getting the second interval, which is pi over 8, that is the h. No, when we divide pi over 8 by 3, we'll get pi over 24. Then the f of a in this case is pi over 4, that's sine pi over 4, plus 4 sine a plus b. That means when you add this pi over 4 plus pi over 2 and you divide it by 2, we'll get 3 pi over 8 plus our f of b, which is sine pi over 2. So from here, we can collect like terms. That's the one that has pi over 4 plus the one that has pi over 4. When we add it together, we'll get 2 sine pi over 4 plus 4 sine pi over 8, 4 sine 3 over 8, 3 pi over 8 plus sine pi over 2. And when we multiply all this, we'll get 1.00013458497 Now, if you look back at the first interval, that means the one they gave us, which is pi over 2, before getting the subintervals, we realize that we got 1.002279877 and the like. So going back to what they said in the formula, that if you get, please move forward, up. Okay, that's, yes, yeah, that, back, please, back. Okay, so if you check what they wrote here, that if you estimate the error and it is less than the specified tolerance, that means we are done. Else, you keep getting the subintervals. Now, when we look at the subintervals that we get, please go back, thank you. We realize that 1.001345 is less than 1.0028. Which says that we are specifically done. So we'll go back to the error formula now that says that 1 over 15 s1 sine x 0 to pi over 2. That's your first one. That's s1, the first interval they gave us, minus the second one, which is the subinterval, is 0 to pi over 4, comma pi over 4 to pi over 2, which is this is 0 to pi over 2. Then we'll subtract these particular values and divide it by 15, which takes us to get this particular value is 0.00143 0.195.0120. So what adaptive quadrature is telling us is that when you get your particular value, that means the one they gave us. If you get a higher number, a particular number, you get sub-intervals. When you do these sub-intervals, it has to be less than, that means the more you split, the lesser numbers you get. So when you get higher numbers, that means you keep splitting until you keep splitting into sub-intervals until you get values that are less than the first value, which is the S1. So until you get that value, that is when you stop getting sub-intervals. So that is just basically what adaptive quadrature is talking about. Do we have any questions? No. So
For the fact that we don't have questions, does not mean we understand what you have presented anyways.
sir?
So you can continue. As
Yes,
in, for
sir.
the fact that we do not have questions,
Yes, sir.
does not mean we understood what you have presented.
So are you saying I should explain again, sir?
So you should continue.
Okay, sir. So, oh God, this is yours. So now let's talk about Gaussian rule or Gaussian quadrature. Now, this particular Gaussian rule is also called probability integral, and it is closely related to the error function. Then it can be computed using trick of combining two to one-dimensional Gaussian. So the Gaussian is another type of quadrature different from trapezoidal and Simpson rule. Just like when we're talking about adaptive quadrature, that we have Simpson rule, we have trapezoidal, but the one we talked about was Simpson rule. So now this particular Gaussian quadrature is saying that we are going to have intervals from A to B. Then W of x, f of x dx is equals to summation of n I is equals to 1 wi f of x I. Now w of x is what we call the weight function, and the x are the nodes. What they are talking about in a layman, like just the way I understand it, is that when we are talking about Gaussian rule, we are saying that we are going to be having polynomial values. We are going to introduce a polynomial values depending on the kind of question that is given. But in this particular one that I want to talk about, we want to find an optimal 2-point formula. Please, can we go to the next slide? Yes, we want to find this particular value, that the integral from 1 to -1 f of x ds is equals to this value. Then where W1 and W2 are the constant value, then f of x1 and f of x2 are the other values. That means in this case, W1, W2, x1 and x2 are the values that we are looking for. So we introduce a polynomial from the one that have the degree of the order of or the precision of 3. So we'll start from x0, x1, x2, that means x raised power 0, x raised power 1, x power 2, and x power 3. So for x power 0, that is 1, x raised power 0 will give us 1. Then we have for x raised power 2, and for x raised to power 3. Now, when f of x is equals to 1, that means when f of x is equals to x raised to power 0, just like my colleague has explained when we're talking about integration, it's saying that when you integrate the value of 1, what are you going to get? If we integrate 1, we'll get x. Now, the interval they gave us was from 1 to -1. So if x, that means this is a definite integral. That means they gave us a value. So if x, when you integrate 1 and you get x, Since you have gotten x, then you input the value of your 1 and minus 1. That means 1 minus minus 1. And 1 minus minus 1 is going to give us 2. So this was how they got the value of our 2. Then for the second one, we'll do the same thing, which is x raised to the power 1. When you integrate x power 1, we'll get x raised to the power 2 over 2. And when you get x raised to the power 2 over 2, you input the value of your 1 and minus 1 and subtract it, then you get the value of your 0. Then when f of x is x raised to the power 2, we'll do the same thing. We'll integrate, we'll get x cubed over 3. Then when we get x cubed over 3, you input the values of your 1 and minus 1, then we get 2 over 3. Then for your x3, we'll do the same thing and get Sam.
Yeah.
Please, can you stop sharing your screen? Let me try to share this one I worked out on my phone. Then do you understand? Can we all see this?
Yes, we can
Yes,
see it.
you can.
Okay, sir. I think this will explain it better, sir. So, like I was saying, I said when we're talking about W the other time, that sounds as a constant, that if we have this particular value, f of x dx is equals to C1 f of A plus C2 f of B. So what we are going to do here is that this particular f of A and B, we are going to make it satisfy the value of x1 and x2. That means we are replacing the value of A and B by x1 and x2. So here we have this. That means f of x dx is equals to C1 f of, instead of f of A, then we replace it by x1. That is x1 plus C2 f of x2. Then moving forward, f of x is equals to a naught. That means this particular value, when you have the C1 and the f of A, you have two particular values, the constant and the x's. So the constant here is a naught. That is a naught plus a1. That's a naught x raised to the power 0. And x raised to the power 0 is 1. So that is why we have purely a naught plus a1 x raised to the power 1 plus a2 x raised to the power 2 plus a3 x raised to the power of 3. So from here, we can input it into the value. Since our f of x is this value, so anywhere you see f of x, you replace it by this value. That is f of x dx is equals to a naught plus a1x plus a2x squared plus a3x cubed dx. So I was talking about when you integrate. So if you integrate the value of your So if you integrate the value of this now, we'll get b minus a plus a1. That means if you integrate this, we have b squared minus a squared divided by 2 plus a2 b cubed minus a cubed divided by 3 plus a3 b raised to power 4 minus a4 divided by 4. Now, from here now, remember we said that we are going to replace our x1, our a, by f of x1 and f of x2. So from here we have C1 open brackets a naught plus a1 x1 plus a2 x2 squared plus a3 x1 cube plus, that's the value of your C1. Then for your C2 now, a naught plus a1 x2 plus a2 s2 squared plus a3 s2 cube. Now for this value, that means for a naught and a naught, we say that C1 and C2, that means if you open the brackets, we have a naught C1 plus A naught C2. So we can say A naught is common to both of them. Then you bring out, you factor out C1 plus C2. Then you do that for, if you factor out A1, then C1x1 plus C2x2. Then plus, when you open the bracket for C1 A2 x1 square, if you factor it out, A2 is common, then C1 x1 square plus C2 x2 squared. Then you do that for the last one, that's A3 C1 x1 cube plus C2 s2 cube. Now, in this case, our C1 plus C2 is now B minus A. Then C1 x1 plus C2 x2 squared is B squared minus A squared over 2. Then C1 x1 squared plus C2 s2 squared is equals to B cube minus A cube over 3. Why the last one? That's C1 x1 cube okay. So having gotten this value now, then there's a formula that says that if you want to get our C1, that C1 is equals to B minus A over 2, and C2 is equals to B minus A over 2. That means if you input the value of our A into these values, we'll get 1 minus 1 minus minus to give us 1. So in this case, I will do the same thing. I will get 1 also. So both C1 and C2 are 1. And for our x1, if you input this value, we'll get minus root 3 over 3. And for the last one, we'll get root 3 over 3. So, Sam.
Okay, let me share my screen.
Yes.
Okay. Thank you. So we'll go to composite rule. Composite rule. In composite rule, in this integration, we'll try to divide the integration interval into sub-intervals, and we use simple integration rule for each of those intervals. So let's look at what we are trying to say. Have a look at the function f of x equals to s squared plus 1 raised to the power of 17. So we can think of this function as being the result of combining two functions. If gx is equals to s squared plus 1 and h times t is equals to t17, then the result of substituting gx into the function h is h times gx equals to gx17 equals to s squared plus 1 raised to the power of 17. Another way we can represent this would be like this diagram we have below. If we have x, let me move to the second slide. So we start off with x. The function g takes x to s squared plus 1, and the function h then take s squared plus 1 to s squared plus 1 raised to the power of 17. Combining two or more functions like this is called composing the function, and the resulting function is called a composite function. Let's go to the next slide for a clearer understanding. Using the rule that we have introduced so far, the only way to differentiate the function f of x equals to s squared plus 1 raised to the power of 17 would involve expanding the expression and then differentiating it. So if the function was x squared plus 1 raised to the power of 2, if we want to expatiate it, what we are going to have is x squared plus 1 multiplied by x squared plus 1. Then this would not take long to expand these two, because it is just x squared plus 1 raised to the power of 2. But if we have to expatiate this kind of the differentiation formula, that means we have to do it 17 times. This will take us a longer time to expand. So if we say f of x equals to x squared plus 1 to the power of 17, it will take us a longer time. So we need to look at using composite rule to make this kind of formula quicker to solve. Instead of expatiating x squared plus 1 times x squared plus 1 times up to the 17th times, if we use a composite rule, this kind of formula, we can actually solve it quicker. So let's look at what composite rule tells us. Composite rule is also known as chain rule, and most material I looked, they were all referring it as rule 7. So composite rule is also known as chain rule. What does it tell us? If f of x is equals to h multiplied by g of x, then f prime of x is equals to h prime times g of x times g prime x. In words, what it means is we differentiate the outside function, then we multiply by the derivative of the inside function. I don't know if you understand. What is trying to tell us is what? We differentiate the outside function. What is the outside function? The outside function is h. So we differentiate it. It gives us h prime g of x. Then we multiply it by the derivative of the inside function. What is our inside function? Our inside function is this g of x. So when we differentiate it, what we will derive at is g prime x. So if we bring this composite rule or this composite formula into this f of x equals to x squared plus 17, then our outside function, which is h, will be, which is 8 dots. This 8 dot in bracket, this is just I don't want to bring out the inside function. That is why I kept this inside function as a dot. So I want to treat only the outside function, which is this bracket all over 17. So what I'm doing is I will derivate it, and what I will get from the explanation of differentiation will bring the power and multiply it by the function, then reduce the power by 1. So what I've done is, this is just the outside function that I've dealt with. The inside function is, which I present as this dot, is x squared plus 1. I've not treated that yet. What I've just done is only the outside function, which is what is inside this function over the power of 17. So this is what I derive from it, which is 17 bracket this dot raised to the power of 16. Then I will now go next into the inside function g of x. What is my g of x? My g of x is x squared plus 1. If I derivate this, what I will come to, if I differentiate it, what I will get, remember I said we'll bring this power, this s squared, which is this 2, which is the power of it, we'll bring it and multiply it by the function. And from our constant rule in differentiation, we say any constant is equals to 0. So this derivation will now give me 2x. That means I don't need this constant. I've thrown it away, which gives me 2x. So composite rule tells us that if I combine this both outside function and the inside function, what I'm going to get in this differentiation that we are doing is 17x squared plus 1 times 2x. I don't know if we get it. So what I'm trying to, what I've differentiated is what this rule has just told us. Let me go to another example. So let us differentiate the function 1 divided by s cubed plus 4s squared minus 4 plus, sorry, I'm calling zx. 1 divided by z cubed plus 4s squared plus 4z squared minus 3z minus 3 raised to the power of 6. We can rewrite this with that simple example. So let's rewrite it as z cubed plus 4s squared minus 3x minus 3 raised to the power of minus 6. Then what is the outside function? The outside function, as I illustrated, is this bracket raised to the power of minus 6. I'm not treating the inside, this is the inside function. So I will present this inside function as a dot. So I can bring out this my minus, this power of minus 6, which when we differentiate, what we will get from our differentiation rule, we say we should, our power rule says, bring down what we have here, multiply by the function, and reduce it by 1. So when we do this, what we'll get is minus 6 times the inside function, which is presented as a dot, minus 7. Now we will now go to our inside function. We'll differentiate what we have inside. This is our inside function. So our inside function is z cubed plus 4s squared minus 3z minus 3. When we differentiate it, we'll derive 3s squared plus 8z, that is this, we are bringing these 2 and we are multiplying it by our function, giving us 2z minus this 3z, which is this. Then when we combine it according to our chain rule, what we are going to have is, already we have minus 6 raised to the power of minus 7. So what we have here is minus 6, which what we derive from our inside function, which will be here, raised to the power of minus 6, sorry, let me come again. Minus 6 multiplied by our inside function, raised to the power of minus 7 times what we derived from our inside function, which is this. That is what power rule is trying to do here. So let's also see an alternative formula that we can use for our power rule. If y is a function of u and u is a function of x, then we can state that our composite rule can be dy dx equals to dy du multiplied by du by du dx. This makes the rule very easy to remember. So let's proceed. We'll solve some examples. While solving these examples, we would understand this alternative formula that says that dy dx is equal to dy du multiplied by du dx. So the expression dy du and du dx are not really fractions, but rather they stand for the derivative of a function with respect to a variable. However, for the purpose of remembering the chain rule, we can think of them as a fraction so that du cancels from the top and bottom, leaving just dy dx. So let's take this example. If we differentiate y is equals to s squared plus 1 over 17, we can state that our u is our inside function, which is s squared plus 1, so that our y will be our outside function, which is this bracket. We are only trying to bring out this bracket all over the power of 17. So this is the formula. It states that dy dx is equals to dy du multiplied by du dx. Now, let's look at this formula again. Our outside function. This is our outside function. If we bring our power rule here, we'll bring this 17 down, multiply by the function, then reduce the power by 1, which gives us 17u raised to the power of 16, multiplied by our inside function. So when we differentiate our inside function, which is du dx, what we have here is 2x. So when we bring down our answer, we need to bring out what we have inside this function. So we have 17 multiplied by s squared plus 1 raised to the power of 16 times 2s, which gives the same result as that first formula that we actually solve. But this one, dy dx equals to dy du multiplied by du dx, can help us remember. All we are just trying to do is make us remember that if we have this function, we can split them into dy du by dy dx. So that is what we have, sir. Is there any question from anyone?
So you skip the error formula.
We included the error formula in the adaptive quadrature. When we were treating adaptive, we also treated error. So that's what we use as our error formula.
Okay, do you have questions? All right. Well, we assume that everyone. Oh, is there any question? All right. So, well, if you have any question or any other issues, you could go to the YouTube channel to look at the class, so that at least you could refresh in your memory.